I think I'm just gonna slowly let the shelf behind me fall apart into like a bigger and bigger mess as the semester goes on. I've already lost. This is Gideon. This is my son's drawing of the periodic table. He designed flasks for all of the elements. So normally I would just put this on my office door, but instead it's here. So slowly everything's gonna fall apart back here. You can watch the deterioration happen in real time. Anyway, let's talk about carboxylic acids. Carboxylic acids are going to be chapter 17. It's kind of a nothing chapter. There's not really a whole lot to say about this chapter. There's a couple of important reactions for sure, and reactions that we'll use, especially when we get to the enolate chapters later on. So it's worth talking about. There's some oxidation reduction stuff just to kind of reinforce things that we've already talked about. There's a little bit of organometallics, so it kind of fits in here, but there's just not a whole lot to say. It is a really nice springboard into the next section that we're going to talk about, though. So we're going to throw some carboxylic acid stuff at you. This will probably only be one video for this chapter, although depending on how long I talk, if I get distracted by whatever, it may go to 2 videos, but it'll probably be 1 video and we'll just get through everything relatively quickly. So carboxylic acids. So you know carboxylic acids in general, we know what the functional group looks like. It is carbonyl with an OH group all attached to the same carbon. And of course, these are just a higher oxidation state than aldehydes or ketones. We have more oxygens attached to the carbon. The first thing to know about carboxylic acids is that they are acids, right? If we react them with a base, right, we can remove this hydrogen and make the conjugate base. And the conjugate base of a carboxylic acid is resonance stabilized. It's pretty stable. And so if you have a base, it will almost always remove the hydrogen from this position. Right? So if we treat a carboxylic acid with a base, we expect to get, right, the conjugate base. You get whatever else over here. If we treat a carboxylic acid with acid, oops, oh no, now I got 2 I's in there, help. Or H plus, right? We know where that hydrogen is going to go because we've just been talking about this. The most stable position for that hydrogen to be added is the carbonyl oxygen, and so we'll get something that looks like this. Now notice that this is also resonance stabilized, and the resonance form is actually kind of interesting because it becomes symmetric, where you have carbocation with 2 alcohols attached to it, right? And so this gets kind of weird and interesting things happen, and we'll talk about that here in a minute. But if you add base, you're going to remove the hydrogen from the OH. If you add acid, you're going to add the H plus to the oxygen. So the first thing to know about carboxylic acids is, of course, mostly the main thing that we use carboxylic acids for is they are acidic. They're a source of H plus, right? We can have them add H plus to whatever base we use. Okay, so that's not terribly exciting. How do we make carboxylic acids? Well, we know one way is oxidation, right? We can take a primary alcohol and treat it with chromic acid, H2CrO4, and we will oxidize that alcohol up to the carboxylic acid, right? Chromic acid is a very strong oxidant. It will oxidize the alcohol. You can also do this with an aldehyde, right? If you have an aldehyde as your starting material, you can also use chromic acid for that. And that will give you a carboxylic acid. So if you need a carboxylic acid in your molecule, you don't have one. One way that you can do it is you can, if you have an alcohol or an aldehyde present, you can oxidize those using chromic acid, add some more oxygen-carbon bonds, and get to the carboxylic acid as the product. You can also use an organometallic reagent. You can also use a Grignard reaction to make a carboxylic acid. So if you have a Grignard reagent, and let's quickly recall what a Grignard reagent is, right? Grignard reagent is some carbon-magnesium bond, right? Like that. You can treat this with CO2. So CO2 is just a carbon that has 2 carbonyls, so carbon-oxygen double bonds. And this is going to react exactly the same way that we would normally expect, right? The electrons from the carbon come and attack the carbonyl carbon. we break the carbon-oxygen pi bond and create a lone pair on one of the oxygens. And what we get out from this now is going to be a negatively charged oxygen up here with the magnesium bromide as the counter ion. Right? And then we'll treat this with H plus, and we're going to get the carboxylic acid. Okay? So we've added a carbon to our R group. However many carbons, let's say that we had like a benzene ring here. If you have just phenyl magnesium bromide, you have a benzene ring here, 6 carbons. Your final product would be benzoic acid. It would have 7 carbons, 6 carbons in the R group, plus 1 additional carbon. So if we want to create a carboxylic acid and we don't mind adding carbons to our structure, we can do that by creating a Grignard reagent and then having it add to the carbonyl of carbon dioxide. I've done this lab in teaching organic 2 before, where you take some solid CO2, some dry ice, treat it with your Grignard reagent. It works pretty well. The resulting intermediate, the one with the negative charge on it here, this one kind of looks like snot, so it's really gross. But it's easy to tell when your reaction is done. When it looks disgusting, then it's pretty complete. So a pretty easy reaction to do. You make a Grignard reagent, and then so treat an alkyl halide with some magnesium, make a Grignard reagent, add some dry ice. The whole thing ends up looking like snot. You add some H plus to it, and you got yourself a carboxylic acid. So that's one way to make a carboxylic acid. Once we have a carboxylic acid, there are reactions that we can do with those carboxylic acids. I'm going to highlight 2 of them. The first of them is reduction. And we're going to reduce carboxylic acids with our old friend lithium aluminum hydride. And the second one is decarboxylation. This is a new reaction and one that we will return to later in the course. So, whoops, this is minus CO2. So this is kind of like the opposite of the synthesis that we just did. All right, so if you have a carboxylic acid and you treat it with lithium aluminum hydride, you are going to reduce the carboxylic acid. We're going to add H minus. Remember that lithium aluminum hydride is just a source of H minus. H minus is going to add in here. And you're going to get something like this. And now, in previous examples, we've just kind of stopped here. But what happens is actually this negative charge reforms and kicks out the OH group as a leaving group. Right? And it'll make an aldehyde. Now you've got an aldehyde and you've got lithium aluminum hydride around, and we know what happens then. H minus adds in there, and we get ourselves a primary alcohol. Okay? After we treat with H plus, and then you add H plus as a workup, and you get the primary alcohol that looks like this. So carboxylic acid can be reduced to a primary alcohol using lithium aluminum hydride. It always goes all the way to the alcohol, right? We can't stop halfway at the aldehyde just because lithium aluminum hydride is too strong of a reducing agent. It will not stop halfway through. So if you have a carboxylic acid and you want to make an aldehyde, you have to first reduce it using lithium aluminum hydride all the way down to the alcohol, which is the process I just showed you. And then you have to do like a PCC oxidation to make the aldehyde. So it's a 2-step process to go from carboxylic acid to aldehyde. You have to reduce to the alcohol and then oxidize again. So keep that in mind. Decarboxylation is a kind of a subset of reactions. It only happens for a particular type of carboxylic acids, and that's when you have beta carbonyl carboxylic acids. Okay, so what does that mean? So if you have a carboxylic acid, the carbon next to that is the alpha position, and the carbon next to that one is the beta position. So if we put a carbonyl at that beta position, you can put whatever you want here attached to that carbonyl. It can be a ketone, it can be an ester, it can be a carboxylic acid, it can be an aldehyde. It doesn't matter as long as the carbonyl is present. What happens is that this is actually ends up being, I'm going to redraw this, just kind of rotating one of the bonds. this ends up being a situation where you end up with this hydrogen bond. And so what I've done is I've just rotated this OH group up so that it's pointing up, and I've rotated the carbonyl group so it's pointing down. So this is the same compound. And what you end up with is you end up with this oxygen lone pair on the carbonyl is kind of pointed right at the hydrogen here. And so what you can do is you can draw a mechanism here where this oxygen lone pair goes and gets that H plus. Carboxylic acids are acids, right? So they're going to give away H plus. Carbonyls are good bases. They can pick up H plus. So if those two things are next to each other, it makes sense that this is what's going to happen. Right? So nothing is surprising so far. So we can get that H plus, and instead of just making a lone pair on the oxygen, I'm going to make a pi bond here. So this is like an elimination reaction. And then we're going to make a pi bond here. I'm just going to keep pushing these around. And then this is going to kind of replace the lone pair that we used to grab that H plus. All right, so what overall has happened here is we have made a double bond there. We've got an OH up here, and we've broken this whole group off. And so now what we have is we have double bond to oxygen and double bond to oxygen. Because we broke this sigma bond right here, we end up losing CO2 minus CO2. So what we end up with is we end up with an enol right here, and we end up with CO2. So this is the point in this chapter where I call back to something from Organic 1, and you guys all kind of stare at me and look at me like, oh yeah, I kind of remember that a little bit. So prepare your stares for this one. You remember enols, of course, because enols are just ketones in disguise, right? We can move the hydrogen around. We lose the hydrogen off the oxygen, we add it to the carbon, and what we get here is we get a ketone. Well, I guess assuming that the R group is a carbon, we get a ketone. And so decarboxylation is the loss of CO2, and basically what it does is it gives us a different carbonyl compound. So just like on the previous slide where we gained a carbon, we're doing the opposite here. If we have a carbonyl in this beta position, we can lose CO2 and lose that carbon as well as the carboxylic acid and get a ketone out. And this is going to be really important in the future for reasons that we're going to talk about. But these beta carbonyl carboxylic acids are actually really reactive compounds, and they do a lot of enolate chemistry, which is chapter 19. So file this one away. Remember this one, mark it down, because we're going to come back to the decarboxylation. One important point that I do want to make about decarboxylation here, and this video is already getting long, but this is the last thing I swear, is that if you have a compound that is not a beta carbonyl carboxylic acid, so if you have something like this, right, and you heat it up, you do not lose CO2, no decarboxylation, right? So in a normal decarboxylation, all you have to really do is heat these things up, right? So you'll just see heat as the reaction conditions. You heat them up, and this kind of acid-base reaction starts, and away it goes. You lose CO2. The keto-enol tautomerism occurs here, and you end up with a ketone. Right? So we can heat these up and lose CO2. If we have a carbonyl or carboxylic acid that's not near a carbonyl like that, this decarboxylation does not occur. So it really is a very specific type of reaction that only occurs under certain circumstances, and those circumstances are the presence of that carbonyl in the beta position. All right, that's chapter 17. I did it in almost less than 14 minutes, which is pretty good. So I hope you enjoyed it. We will be back with more carbonyl chemistry soon.